Next up, we have a visionary in the field of AI, none other than Mark Huang, the co-founder and chief architect at Gradient AI. Mark will be gracing us with his wisdom on scaling AI with domain-specific mixture of experts.
Cool. Hi, everybody. Thanks for attending this talk. So maybe an introduction on my part. I'm Mark. I'm one of the co-founders of Gradient AI. We are effectively a language model development platform, although we might take the language model out of that and actually have other modalities up soon. What our experience is API developer platforms and solutions for language model completions and embeddings. Currently, we have a self-service product. We're a seed stage startup, and what I'll kind of be talking to you today about is just some lessons learned and experiences in training like more specific models, smaller models and specialists rather than generalists, and a kind of interesting experiment in architecture that we set up for. It's more of an ensemble, but the mixture of experts approach to being able to set up multiple models under one entry point, and why our platform kind of uniquely solves a specific problem within that space. So I will start with maybe a little of an agenda. I like to start with an agenda just so people can decide whether or not it's worth listening to or not. But yeah, I'll kind of begin with the narrative that the specialist models can be better than generalist models. I don't necessarily believe that they are opposing theories like most people tend to think. They are actually pretty complementary. Some lessons learned in like failing to actually train a mixture of experts and then going with a more like microservices composable approach, and then how do you actually achieve that at the end, specifically using parameter efficient fine-tuning methodologies. To start with, I think a lot of research is coming out, back and forth between, hey, should we be training only on textbooks? Phi 2 just came out from Microsoft. Phi 1 was a really, really interesting example of like overtraining a model for a specific task and then just beating the benchmark and performing better than models that are 2 orders of magnitude larger than it. I think everybody's sort of seen this chart. This is specifically a pretty important paper, the Big Bench paper, mostly because they set up pretty good evals that aren't easy to beat. And I use that as kind of the baseline eval that we kind of keep an eye on. So you will see in this chart that effectively the scaling law behavior of doing nothing on a task, basically always effectively getting almost 0% accuracy or whatever metric you have on that. And then at some point, once you get to like 100 billion parameters in size for a model, all of a sudden it starts actually performing pretty well. I think, and this is the narrative that has been going through, it's more a concept of having like smaller composable tasks that eventually get solved. So if you have a task that requires 10 intermediary tasks to achieve a final outcome, and you have only solved 9 of them, you need that 10th task in order to actually be able to do anything on this evaluation. So more or less, I think it's actually more linear than we think it is, but obviously we need to do more research in the community to kind of understand the capabilities of the models and how that would work. I think I won't spend too much time in this particular chart, but this is also from the same Big Bench paper, and there are some tasks that get worse once you scale up the model. And in particular, on the right side, an independent study with Berkeley researchers where they, kind of talk about the whole concept of model drift. similar to how we always were thinking about things back in the day in machine learning, where eventually the model will get a little bit worse once you do an update on it, or you actually want to choose certain things that you don't really care about as much, and you want to train more and fine-tune the model on the tasks that are more important to you. So I'll bring the attention a little bit more towards an experiment we ran, and like why I think that mixtures of your tokens and mixtures of your data are actually pretty important when you, the more and more you fine-tune the model to expose domain specificity in its abilities and capabilities. So this is just a repeat of the slide that's evaluation that's taken from the Textbooks Is All You Need paper. Punchline is you can actually do pretty well with a small model. Questionable whether or not it was trained on the evals and if there's contamination. Contamination now is a huge problem in the open source, mostly because we don't know if the tokens are now computer generated or not. But that's a whole other subject matter that's a little bit out of the scope for this particular presentation. So what we tried to do is we actually tried to take baby steps in creating a domain-specific financial services model. This is in training a 7 billion parameter model, so that's why you'll see there's only about 200 million tokens. So this is like kind of the first initial experimental phase that we ran through, and we created a corpus and scraped it of analyst reports, SEC filings, Excel formulas specific to finance, and also a bunch of like markdown math. Went through the arduous process of actually getting like tables out of there, because I think that a lot of models, it may not actually be the case that they're bad at math to an extent per se, but doing the symbolic mappings on it, like, I don't know if anybody's tried to extract PDFs, but it's a pain in the butt. And it's never a joy, and it's an adversarial format to an extent, right? Well, the punchline is basically across these tasks, like the MMLU, ARC, Truthful QA, like these are kind of standard evals you'll see on Hugging Face, leaderboards, to how much they're actually valuable to us. I actually use them more so as benchmarks and measurements that show me whether or not, how much I'm destroying the model's capabilities as we train them further and further. So the two tasks that we actually cared about were meet in the middle kind of objective function for Excel formulas in completions that way, and then SEC reports too, where we wanted the model to evaluate a set of 10K documents and then make a classification on, analysts kind of target like upgrade, downgrade, hold, fixed. And we actually see that taking new corpuses and training the model much further causes a degradation in performance, catastrophic forgetting, right? That's always the name of the story. So how do we actually mitigate that aspect of things once you start training more and more? Well, it's about your data mix. It's not so much the fact that you need unique tokens. There are new papers out there. In particular, Hugging Face came out with a great paper about scaling models in data-constrained environments. It's about mixing in the right set of tokens so that you retain a certain amount of knowledge in the model and have it continue to perform on the tasks you care about. So what we did is we filtered out the refined web data set and mixed in 150 million more tokens using refined web, in addition to all of the special domain-specific corpuses that we wanted the model to perform on. So TLDR, what that actually led to was the model maintaining performance across the more generalist benchmarks that you have, in particular language. So out in the wild, a really good example of the concept of catastrophic forgetting, or like how you have to be a little bit more careful about that, is like Code Llama. Code Llama is exactly Llama 2, right? But they further trained it on a substantial amount of code, but they didn't mix in any sort of language tokens inside of it. That actually led it to kind of being a little bit of a failure of a model, in my opinion, because it just doesn't understand language at all anymore. It's only good for code, and it doesn't really help with generalizing a model's abilities on things that it might actually be helpful for when it can understand instruction and language and all of that. So this is just a little bit of an example of like how do we think about in the community the right data mixtures to add into models to retain their ability on different tasks like language or other ones like math. You have like GSM-8K. We don't really have a good sense of that right now. I think there have been papers out there talking about like optimizing those mixes, but just due to the fact that in sort of a call to action, in my opinion, like we need to be releasing more of the data sets into the open along with the weights to be able to go backwards in figuring these things out. So now I wanted to kind of transition from like, hey, we're training like one specific expert to like how do you scale like a bunch of like expert models at scale. You know, a lot of people are talking about, hey, should we be using a bunch of 7 billion parameter models or 13 parameter models orchestrated in a particular fashion rather than maybe using like a 500 billion parameter model. Don't quote me on those exact numbers, but I'm just sort of saying, you know, composability and orchestration, I think, is actually going to become more and more important. This is just a slide to show, you know, on the left, we actually tried to train a switch transformer using a bunch of domain-specific data that we scraped. We just weren't able to do it. Like, that was a big failure on our part. It was an experiment to try to see if we can bring the kind a more composable ensemble of models into an enterprise use case. Maybe you know, companies that want to have their law expert models, their finance expert models, and their you know, operations expert models. Things in the enterprise are a little bit more complex than to say like you know, wanting to have one corpus for everybody. Some of the main problems and issues with that is just training instability, and the fact that when you're training both in this architecture, a router, as well as an LLM, like back propagating the gradients causes like a lot of like non-linear instabilities within the training process. So what we actually think is a little bit more suitable is like kind of more of a microservices approach, where like you have an embeddings model, you train like some base model on the clusters of data that are actually embedded there, and then you decide at query time which one of the experts to route to. So it's kind of a cosine similarity exercise, as well as you know, a fine-tuning exercise as well. So that brings me kind of towards the concept of why we should always try to leverage like embarrassingly parallel methodologies and approaches where we can. In this case, like one of the implementations that we tried was like a more of a cluster train branch merge approach. It's actually really simple. The code is open source. I believe it was developed by Google actually, wherein you can just take one seed LLM, pre-process a bunch of data, a huge set of data that you care about, and then just cluster it. Use any sort of encoder that you want, like BGE large, you can use OpenAI, doesn't really matter. The main thing is like, if you have 5 experts that you want, or 10 experts, or 16, or whatever optimal number, you can take a bunch of these and figure out where the centroids are, so that you can route the models in like a more probabilistic fashion at query time to be able to run your queries on top of. So an example would kind of be like, you know, you embed a bunch of finance or operations engineering or product data within an organization, and then you figure out where your clusters lie. Using sparse networks, though, they still tend to have 2 things that are a little bit less approachable for people who aren't exactly, you know, compute optimal in a way. I would say like people call it GPU poor. But I like to say, like, you don't have as much access to like all the GPUs in the world, right? That's where the new techniques, like I was talking about in the beginning, like LoRa, tend to have a lot more ability to help people unlock some of these use cases. So rather than taking all the weights and changing all the weights necessarily, like there's a time and a place for that. You can just freeze some of the weights and then train like the unfrozen portion of them. The two parameters that are actually important there are like the LoRa rank and then the LoRa multiplier. Usually the multiplier is just 1, saying you're equally weighting all of your LoRa adapters. And that tends to unlock the use case where think of like having 4 servers up at the same time, each one being a custom expert. If you have to keep them all up at the same time, or you want to swap in one expert for another, you go through the cold boot problem where basically you have to load and unload one. So why don't we think about like actually batching the LoRa's together into one large tensor rather than having to separate them out into every single server? So that's a little bit more, I think I want to skip these slides for now. That's a little bit more why you want to do LoRa mixture of experts than anything. I think in terms of some tips that we learned in training like fairly large LoRa's for language models and to serve as experts, we found that like yes, if you train only the query and the value layers, you will avoid more catastrophic forgetting, but you also won't really learn much and make the model much better on like tasks that are a little bit more complex. So you should probably almost always train closer to like QLoRa fashion, where you target like almost all the layers, and then also target for a rank like greater than 32. Anything less than 32, I found has been fairly superficial in terms of its ability to like actually have the model learn more advanced capabilities and perform on more advanced tasks. So over on the right, like there's just some metrics on. Oh, I didn't put the rank on the blue and the orange, but basically just showing that you want to have like a larger rank and also target more layers. The layers actually have much more effect than anything on the downstream performance on like multiple multi-class classification evals that we constructed, as well as like more grounded QA. So how do we actually serve all of these LoRa's? I think that's like the more interesting question. Like once you have constructed your experts, you need a way of serving them that's not going to take like forever, and unless you want to just spin up like 1,000 GPUs at a time. If you have like certain requirements, like wanting to have a lot of concurrent requests, as well as like certain latencies, less than 5 seconds is actually too long for search, obviously, but for this use case, like we wanted to just ground ourselves in like fairly realistic requirements that we could satisfy. Spinning up like a single node, so that's like the more important part, having like a single node to serve like a bunch of LoRa's at the same time, and all of these LoRa's being your experts. I wanted to go into a little bit of background on like what actually matters at inference time. When people ask me like what is the latency, I usually have to respond and say like that's too open of a question, because there are a lot of factors that go into it, and in particular, how everybody should kind of think about it is like there's 2 parts always that you should think about. Is the pre-fill time, which is when the prompt goes into the model, how long does it take for that first token to come out of the model? That's the pre-fill latency. As for the decode latency, that's like what you see when you talk to any of the Copilots or the ChatGPTs or even the Bards of the world, where they're just streaming each token. No matter what anyone says, the decode portion is pretty constrained, even to this day. It's the pre-fill layer using the KV cache that you can actually speed up. So maybe more into kind of the technical aspects of like, okay, what it means to and what you're constrained on in terms of like loading and unloading LoRa's for being able to run inference on experts at runtime. basically you have two things that are going to hold you back, and those are memory bandwidth and network bandwidth. So then what you're really going to be seeing is kind of a stepwise linear loading time, like, you know, scaling for loading times. So it's really like, hey, as you get eight LoRa's that you have to load at a time, or 100 LoRa's, like they just accumulate over time to be able to, that time and latency to load and unload will accumulate over time. So what does it take to actually facilitate like a multi-tenant LoRa architecture? Well, we basically need to consider the fact that every tenant may have a different set of target layers. So you have the Q, K, V projection layers as well, and then maybe different LoRa ranks. You need dynamic LoRa batching. Interestingly enough, the S-LoRa paper came out recently. I think it gave a lot more people insight into what's going on and what are the things that are actually possible when you can do LoRa-based batching. Our product came online end of August, and that was actually what facilitated our ability to do like concurrent fine-tuning requests as well as inference requests on our public service. And that's you know, kind of the secret sauce to an extent of how most of these things work. If you want like multi-tenant LoRa fine-tuning in inference on your service. So this is a little bit of the performance scaling capabilities of you know, what happens when you can batch the LoRa's. What will happen is like something like faster transformer like NVIDIA's Triton, they use static batching, so it's gonna be a lot faster for a batch size of 1, but as you scale up with larger batch sizes, because you are just masking out the set of LoRa's that you want at query time, the larger the batch, it scales sublinearly until obviously you saturate your memory or your bandwidth there. And you know, so what you really want out of these kind of situations are what's the optimal throughput that can occur when you have, you know, thousands of users and thousands of people sending requests to your service. So in a sense, like you can construct like a mixture of experts ensemble within an organization to service like one interface rather than having to do all this orchestration necessarily for other things, and it makes it a little bit more flexible. So that's basically it. Like in terms of the future directions that we were going towards, we still have to go and consider the aspect of like merge ties. So that basically is the fact that not LoRa's aren't like completely orthogonal and completely composable. So if you merge like 5 of them together, what actually starts happening? Like you'll see certain tasks do worse. At a certain critical limit, they get much worse. And how do you go about figuring out like what are the sections and the weights that matter the best for the target task that you're after? And then, like I said, the decoding aspect is probably the most constrained for inference, but how do you actually deal with that when you want to use like speculative coding, which is using a smaller LLM on the side to decide how you want to more optimally decode, more optimally do inference when you have like a bunch of tenants on a LoRa adapter. And then going back to like, can we finally train a router well? That's sort of an open question and something that, you know, within our, at Gradient, we're trying to figure out in order to figure out like, you know, what's the demand for a mixture of experts. And there aren't a lot of open source examples of people being successful at doing that with these models. I think the largest model I've seen is probably like 13 billion in parameters large for trying to train a model that way. So it's a little bit the, you know, debate between sparse networks or like more dense networks. As for like a little shameless plug, you know, I'll introduce our company, or Gradient, and you know, we just provide like an API developer platform for like fine tuning and inference. You know, hopefully you can take a little bit of our lessons learned, avoid them, and then get a little bit more value out of, you know, taking all of your data and trying to customize your models. I think fine tuning to this day is still a little bit of like a ritualistic art. Select few people kind of know it, and then it's mostly, I would argue, because people just aren't able to really tinker around with it, or they don't really have the specialized knowledge to figure out like how to curate the data or like how to specialize and synthesize data for that. So that's about it for what I wanted to talk to. I'll be glad to take some like Q&A right now. I don't know how much time I took up here, but